Previously we talked about theory of electromagnetism and looked at some fancy animations. Now let's experiment by heating steel, melting aluminum, and levitating copper with high-frequency magnetic fields.
To explore induction heating, we'll use aluminum and steel disks with different diameters. The theory says that for every set of parameters like diameter and conductivity, there exists an optimal frequency for heating metal using the induction. Since we have a fixed frequency, different diameter workpieces are expected to warm up at different rates. We start with steel disks with a coil which produces an alternating magnetic field of 8 kHz frequency. The current in coil is slowly raised from 270 amperes to 500 amperes. And as metal starts to heat, we can even see the effect of thermal expansion, which when I saw the footage for the first time was a surprise for me. And indeed, a temperature increase of 1000 degrees changes the volume by 3.3%, which is visible in camera. The red glow from thermal radiation is first seen in the largest of the disks. This starts at a temperature around 600 degrees Celsius. The second disk follows, and after 6 minutes, an equilibrium is reached. Filming this without HDR is quite difficult, since the hottest object affects automatic white balance. Nevertheless, we see that largest disks are the hottest. Before drawing any conclusions, let's try a different frequency and use 17 kHz for heating. After the first round, the stainless steel surfaces are now oxidized and darker. This time, the largest piece again warms up the first, but overall heating happens quicker in all disks. Soon after, the next workpieces follow and overall higher temperatures are reached, and more importantly, smaller workpieces are also heated to red hot. Overall, this looks very impressive, and radiated heat is felt even when I was filming this from 20 centimeters away. Thermal camera shows over 1000 Celsius on the hottest object. But taking these pictures is not so simple, because the actual emissivity of material is not known, especially for steel, whose surface properties change when heated. For the purpose of the video, we can use this chart, which approximately correlates the color of radiating black body to temperature of the surface. Judging by these colors, we have surpassed the 1000 Celsius mark. And if we had put on some heat insulation, we could even melt the steel with available power. Next, let's take 4 aluminum disks. They have higher electrical conductivity and lower melting temperature. When we turned on the inductor, something unexpected happened. The aluminum disk flipped. We tried it again by raising the current more slowly this time, but the result was the same. This observation shows that there are also forces exerted on the conducting objects in alternating magnetic field. To solve this, we just added a heat-resistant glass used in fireplaces on top of the inductor. Disks are now fixed into place and heating up. In the first try, the camera failed, so we started the heating process again, and that explains the not-so-shiny surfaces in the second try. In just 90 seconds, we have liquid aluminum which melts at 660 degrees Celsius. Again, the largest disk melted the first and started glowing red hot. Temperature estimate is around 950 degrees in this case. Shortly after the metal cools down, it shrinks again, which is visible in camera. Metal was pressed against the glass, however removing it was quite easy, and the glass wasn't even damaged by the molten aluminum. Props to the manufacturer. In the beginning you saw aluminum disc being lifted by electromagnetic forces. If we take a different coil, which has a funnel shape at the bottom, and an extra loop of coil at the top with a reverse current direction, we can levitate small stuff. What kind of stuff? Everything that has high enough electrical conductivity. We start by aluminum disc, and look what happens when we turn on the current. It levitates and swings in the inductor. After launching it in, we stabilize it mechanically, and we raise the current, so the equilibrium point of net zero force is higher in the coil. We can do the same with a copper pipe. If we throw it in, it starts oscillating, and overall the shape is not so stable. Over time the pipe starts to heat up, which you can see as a change of the color of the surface. Next up, let's take a more complicated shape. 2 joint 90-degree copper turns are put in the levitation coil. You can see the first stable position, but in total it actually has 2 stable states of levitation. And when it's mechanically pushed to the second one, it heats the bottom part. The reason for that is that there is stronger magnetic field lower in the coil, which we're going to exploit later. When copper pieces were heated up, they lost the lift, even though the current wasn't changed in the main coil. This is explained by a change in electrical conductivity, which worsens in metals with temperature rise. Also tried to levitate 2 x 2 x 2 cm copper cube, but it was a too inefficient form to levitate. since solid objects have more mass than hollow ones, but the current and the lift only happens in a thin layer around them. This is explained by a skin effect, which I covered in the previous video. Copper is heavy. Let's see if it happens with a lower density metal like magnesium, which we happen to have in our laboratory. Since the piece is a sphere, it was floating in an inductor with a lot more stability. However, it was interesting to observe that it was slowly spinning up. To slow the rotation, we used another neat trick and took a permanent magnet, which we placed next to the sphere. So there is a stationary magnetic field which dampens the movement of conductors, and in this case, slows the sphere's rotation. But let's go back to aluminum. With the previous coil, we managed to melt aluminum. So what happens when we do it while it's levitating? We start with a bigger aluminum piece and we wait for it to melt. It does not work right away. So we push the aluminum lower into the coil where there is significantly higher magnetic field. And then it starts melting. Then a problem arises. Right in the center, there are no forces acting upon it. So the metal is held up only by the surface tension. In this case, metal slowly starts to leak out. And after losing the mass, the remaining part becomes unstable and crushes into the bindings, causing a little short circuit. We made fine adjustments and proceeded to experiment with a smaller aluminum piece. And this time we were more successful. The little ingots melt more evenly and it's held together also by surface tension forces. In a minute after melting, it begins to glow due to thermal radiation. It was stable and judging by the color, the temperature was close to 1000 degrees. Overall, this is a spectacular view. A molten metal is kept hot and held in the air by electromagnetic forces and nothing more. This can happen because of the special shape of the coil, which results in the net forces pushing inward and upward. Scientists use this levitation melting method to manufacture really pure alloys. This method, when scaled up, gets increasingly difficult to carry out. That's why there are scientists modeling such problems numerically, as well as experimentally. For example, our colleagues in Hanover managed to levitate a half a kilo of aluminum using not one, but 2 coils. For more thorough reading on modeling levitation, I have included the papers and websites in the description. I hope you enjoyed this video and maybe learned something new. And if you want to see more videos with induction heating, subscribe and check out the suggested video on screen. See you there!